Class, today we're going to talk about determinants. Determinants are scalar values that can be computed from square matrices. They give us information about matrices that can be useful for solving linear systems of equations, for computing the inverse, and for some other topics that we'll get to over the course of the next couple of weeks. At the moment, they may seem like a fairly boring thing to compute, but their utility will become more obvious as we continue in the course. Alright, so let's talk about determinants. The determinant of any square matrix is a scalar value that can be computed from the elements of the matrix. It encodes specific properties associated with the linear transformation that the matrix will be responsible for. Since every matrix has only one determinant, we can think of the determinant as a function that takes in a square matrix and gives us back a scalar value. One very special property of the determinant is that if the determinant is 0, then the matrix is singular and does not have an inverse. We'll come back to that a little bit later in the course. First, we need to talk about how you calculate a determinant. Computing a determinant is simple for 1 by 1 or 2 by 2 matrices. For a 1 by 1 matrix, the determinant is simply the value of the only element of the matrix. That's real simple. For a 2 by 2 matrix, the determinant is equal to the top left element times the bottom right element minus the top right element times the bottom left element. For a larger matrix, things get complex, and we actually define the determinant recursively. The determinant of a 3 by 3 or larger matrix is defined as the first element times the determinant of the matrix that you get when you throw away the first row and the first column, minus the second element times the determinant of the matrix that you get when you throw away the first row and the second column, plus the third element times the determinant of the matrix that you get when you throw away the first row and the third column, etc., until you've done this for each element in the top row. Note also that it alternates from subtracting and adding these values. The easiest way to understand a determinant is to work through some examples. If we have a really boring matrix with only one element, for instance, b equals 6, the determinant is simply the value of the only element. Let's go on to our first case where the determinant actually has a useful definition. Let's make a 2 by 2 matrix C with elements 1, 3, 4, 6. In this case, our definition tells us that the determinant of a 2 by 2 matrix is equal to the element A11 times A22, so that's 1 times 6, minus the element A12 times A21, so that's 3 times 4. And of course, this is all equal to negative 6. Alright, straightforward so far. But it's when we start getting to larger matrices that things really get complex. So let's start with a 3 by 3 matrix. I'm just setting D equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, so that it'll be really easy to see what we're doing. If we look at our definition, the determinant of a 3 by 3 matrix will be equal to the first element, so that is 1 times the determinant of M11, which is the matrix we get when we delete the first row and the first column. Note that this matrix M11, which is equal to 5, 6, 8, 9, is referred to as a minor matrix of D. Now, following our rule, we know that we want 1 times the determinant of that minor matrix 5, 6, 8, 9. Then we subtract off the second element times the determinant of the minor matrix 1, 2, which is the matrix we get when we delete the first row and the second column. So that is equal to 2 times the determinant of 4, 6, 7, 9. And finally, we add the third element multiplied by the determinant of the minor matrix we get if we delete the first row and the third column. So that is equal to 3 times the determinant of the matrix 4, 5, 7, 8. Next, we need to actually calculate the determinants of all of those 2 by 2 matrices to figure out the actual value of the determinant of D. But calculating the determinants of 2 by 2 matrices, as we just saw, is quite easy. The determinant of 5, 6, 8, 9 is 5 times 9 minus 6 times 8. The determinant of 4, 6, 7, 9 is 4 times 9 minus 6 times 7. The determinant of 4, 5, 7, 8 is 4 times 8 minus 5 times 7. So we can now simplify this to the determinant of D equals 1 times negative 3 minus 2 times negative 6 plus 3 times negative 3, which is equal to 0. Okay, so that is a little bit time consuming, but really not too complicated. Now what happens if we want to compute the determinant of a 4 by 4 matrix? Well, we basically go through the same process. Let me walk you through it a little bit more quickly so we don't waste too much time. For simplicity, we'll again start with a matrix that just has increasing values in each element. So how do we compute the determinant of E? Well, again, we start with the first element times the determinant of the minor matrix we get when we delete the first column and the first row. Then we subtract off the second element times the determinant of the minor matrix you get by deleting the first row and the second column. And then we add the third element times the determinant of the minor matrix we get when deleting the first row and the third column, minus the fourth element times the minor matrix we get by deleting off the first row and the fourth column. Okay, so far it is fairly similar to what we did before. The trick is that now we have to go through that same process to compute the determinant of each of the 3 by 3 matrices inside. By expanding out every 3 by 3 matrix using the same rules that we applied before, and then we need to compute each one of the 2 by 2 matrices. So hopefully you can see that computing the determinant for one 4 by 4 matrix requires computing the determinants of 12 2 by 2 matrices and making sure to add, subtract, and multiply them appropriately. It's fairly tedious. So in summary, computing the determinant of a 2 by 2 matrix is easy. Computing the determinant of a 3 by 3 matrix can be a little bit annoying, but is quite tractable. Computing the determinant of a 4 by 4 matrix is a huge pain in the ass, and computing anything from a 5 by 5 matrix on up is possible using the exact same approach, but is so obnoxious that I would never do it by hand. However, a computer can do it for us almost instantaneously. For instance, I just asked my computer to compute the determinant of a 500 by 500 matrix, and it gave me the answer without having to wait at all. Alright, so we've determined that we can compute a determinant by hand, but it's annoying with anything larger than a 3 by 3 matrix. We'll also agree that we can, however, compute even the determinants of really large matrices quite painlessly with a computer. But why? Why do we care about determinants? Well, for one thing, there are a lot of special rules for determinants. Some of these may not seem very important right now, but they can be quite useful for simplifying matrix calculations. So let's just go through them quickly. If you remember what an upper triangular matrix is, and I put one up there to jog your memory, then the determinant of any upper triangular matrix is simply equal to the product of the entries along the diagonal, which I colored in red. It follows from this statement that the determinant of the identity matrix must be equal to 1 because the identity matrix has only 1s along the diagonal. Another rule of determinants is that if a square matrix has 2 identical rows, the determinant must be equal to 0. This is related to the linear independence of a matrix, which is something we will talk about later in the course. The determinant of A is also always equal to the determinant of A transpose, and the determinant of a square matrix A times another square matrix B is equal to the product of the determinants of those 2 matrices. The determinant of the inverse matrix of A is also equal to 1 divided by the determinant of A. And in what might be the most important rule of determinants, if the determinant of A equals 0, then A is singular and it does not have an inverse. We talked in the last lecture about finding the inverse of a matrix. We can use the determinant to determine if it will even be possible to calculate the inverse for our matrix. This can thus potentially save us a lot of work. Another really great use of determinants is in the solution of systems of linear equations. Determinants can be used to solve systems of linear equations using an approach known as Cramer's rule. Cramer's rule states that if A is a non-singular n by n matrix and B is an n vector, then the linear system A times x equals B has the unique solution that x equals a vector of elements, where each element is equal to the determinant of the matrix Bj divided by the determinant of A, and Bj is the matrix you get when you replace the jth column of A with the B vector. Alright, that sounds a little bit complicated, so again, Let's test it out to see how it works in practice. And let's test it out while thinking about plants and photosynthesis. We know that plants use energy from the sun to combine carbon dioxide and water into glucose and produce oxygen in the process. So we can write out a chemical equation for this. Some number of carbon dioxide molecules plus some number of water molecules produces one glucose molecule while releasing some number of oxygen molecules. Many of you may already know what the stoichiometric balance is for photosynthesis, but let's use Kramer's rule to actually calculate it. First, we will write out mass balances for each element. For oxygen, we can see that 2 times x1, which is the number of carbon dioxide molecules, plus 1 times x2, which is the number of water molecules, must be equal to 6 plus 2 times the number of oxygen molecules. For carbon, 1 times x1 plus 0 times x2 plus 0 times x3, and for hydrogen, 0 times x1 plus 2 times x2 must be equal to 12 times 0 x3. Now, if we simply subtract the x3 terms from both sides of all equations, we see that we've got a nice differential equation that we can convert into a matrix equation and write out as Kramer's rule dictates. We have a 3x3 matrix A, a 3-vector X, and a 3-vector B. Now this is actually a pretty easy system of equations to solve, no matter what approach we use, and this one would probably be easier to solve by our previous method of elementary row operations. But let's go through it to see how Kramer's rule works, and of course to actually see if Kramer's rule works. Okay, first let's calculate the determinant of A. The determinant of A equals 2 times the determinant of 0, 0, 2, 0 minus 1 times the determinant of 1, 0, 0, 0 plus negative 2 times the determinant of 1, 0, 0, 2. The determinant of the first two 2x2 matrices is 0 for both, which you should be able to figure out pretty easily. The determinant of the third matrix is 1 times 2 minus 0 times 0, which of course is 2. So that means that the determinant of the entire 3x3 matrix A is negative 4. Alright, next we need to figure out the determinant of B1. We define B1 as the matrix A in which we've replaced the first column with the B vector. The determinant of B1 will be equal to 6 times the determinant of 0, 0, 2, 0 minus 1 times the determinant of 6, 0, 12, 2 plus negative 2 times the determinant of 6, 0, 12, 2. Again, the determinant of the first two 2x2 matrices is equal to 0, and the determinant of the third 2x2 matrix is equal to 6 times 2 minus 0 times 12, which is equal to 12, so the determinant of B1 is equal to negative 24. Now that we've calculated the determinant of B1, we can calculate that x1 equals the determinant of B1 divided by the determinant of A, so that is negative 24 divided by negative 4, which is equal to 6. So now we know that x1 is 6, and there are 6 carbon dioxide molecules in the equation above. Next we take matrix A and replace the second column to create B2, and then we compute the determinant of B2. I'm not going to walk through all the details, but again the determinant of the first two 2x2 matrices are equal to 0, and the determinant of the third matrix is 12. So the determinant of B2 is also equal to negative 24. If the determinant of B2 equals negative 24, then x2 also equals 6. Finally, we define B3 as the matrix A with its third column replaced by the V vector. This time, when we compute the determinants of all three matrices, the determinant of the first matrix is negative 12, the determinant of the second matrix is 12, and the determinant of the third matrix is 2. So we have 2 times negative 12 minus 1 times 12 plus 6 times 2, so the determinant of B3 is also negative 24, and x3 also equals 6. So let's go back to our initial system of equations and check if this works. Does 2 times 6 plus 1 times 6 equal 6 plus 2 times 6? Yes. Does 1 times 6 plus 0 times 6 equal 6 plus 0 times 6? Yes. Does 0 times 6 plus 2 times 6 equal 12 plus 0 times 6? Okay, so that actually checks out. Cramer's rule works, and we figured out that 6 carbon dioxide molecules and 6 water molecules are consumed to create 1 glucose molecule, and 6 oxygen molecules are evolved in the process. Okay, so that was one important use of determinants. One nice thing about this approach of solving linear systems of equations is that we can pretty easily just plug all of these calculations into a computer and solve systems of equations without even really thinking about it. Another useful thing that we can do with determinants is compute the inverse of a matrix. The inverse of a non-singular square matrix A can be computed as 1 over the determinant of A multiplied by the adjoint of A. But of course, before you apply that equation, we're going to have to talk about what the adjoint actually is, and that'll take a moment. Let's start by remembering what a minor matrix is. I mentioned minor matrices very briefly when we were defining the determinant, but let me define it more clearly here. The ij minor matrix of A is the matrix that you get when you take the matrix A and delete the ith row and the jth column. For instance, the minor matrix M11 is the matrix you get when you delete the first row and the first column from A. The Mn1 minor matrix is the matrix that you get when you delete the last row and the first column. The Mnn minor matrix is the matrix that you get when you delete the last column and the last row. The next thing that we need to define is a cofactor. Cofactors are defined such that the cofactor aij is equal to -1 to the I plus j times the determinant of the minor matrix ij. So each cofactor alternates in multiplying the minor matrix determinant by -1 or 1. If you're paying attention, we've already computed the cofactors. The determinant of a matrix is really just the sum of the cofactors for the first row of the matrix. We can also define a cofactor matrix that basically just computes the cofactors for each element of the matrix and puts those cofactors in a new matrix of the same size as A. The adjoint is then defined as the transpose of the cofactor matrix. So basically, to compute the adjoint, you need to go through and define each minor matrix and compute the cofactors. Then after you've computed the adjoint matrix, it is pretty easy to determine the inverse. Let's give this a try for a 2x2 matrix first, because it's actually really easy for a 2x2 matrix. We'll try to find the inverse of the matrix 1, 2, 3, 5. First, we'll compute the determinant, which is equal to 1 times 5 minus 2 times 3. So, it is equal to -1. Next, we need to compute the adjoint of B. The element in the top left of the adjoint matrix should be the cofactor B11, so the cofactor of the top left element. So we look at that element, delete the first row and the first column, and we're left with a matrix of just 5. So we need the determinant of 5, which is 5, and then to get the cofactor, we multiply this determinant times -1 to the 1 plus 1. So the first element of the adjoint matrix is equal to 5. Next, we'll note that since the adjoint is the transpose of the cofactor matrix, if we want the adjoint element 1, 2, we need to take the cofactor of position 2, 1. So we're now eliminating the second row and the first column, and we calculate that B21 equals -1 to the 1 plus 2 times the determinant of 2. So that element of our adjoint matrix is -2. Next, we want the cofactor of the top right element, so that is equal to -1 to the 2 plus 1 times the determinant of 3. And finally, we want the cofactor of the bottom right element, which is -1 to the 2 plus 2 times the determinant of 1. Okay, now we've got the determinant and the adjoint, so we can compute the inverse. The inverse is simply 1 over the determinant times the adjoint. So it is equal to 1 over -1 times 5, -2, -3, 1, which is equal to -5, 2, 3, -1. Alright, let's check to see if this works. We'll multiply B times B inverse. The product of these two matrices is equal to 1 times -5 plus 2 times 3, 1 times 2 plus 2 times -1, 3 times -5 plus 5 times 3, and 3 times 2 plus 5 times -1. So if we simplify that, we find that the product of B and B inverse is equal to 1, 0, 0, 1, or in other words, it is equal to the identity matrix, which means that B inverse really is the inverse of matrix B. You probably noticed that these calculations were pretty trivial for a 2 by 2 matrix because the minor matrices were always just a single value. We can actually expand on this to really easily come up with a simple formula for the inverse of a 2 by 2 non-singular matrix. If A is equal to WXYZ, its inverse is equal to 1 over the determinant of A times Z, negative X, negative Y, W. Nice and easy formula to use for 2 by 2 matrices. Alright, really quickly, without going through all the steps, let's use this approach to figure out the inverse of a 3 by 3 matrix. We'll call our matrix C and set it equal to 1, 2, 0, 1, 0, 2, 0, 1, 1. Alright, first we need to compute the determinant. But we've worked through the calculations for a determinant already, so I'm not going to waste time doing the calculations, but you should be able to check this for yourself pretty easily. The determinant of C is equal to -4. Next we need to calculate the adjoint of C. The first element will be equal to the cofactor C11, which is equal to -1 to the 1 plus 1 times the determinant of 0, 2, 1, 1, which is equal to -2. The second element is equal to the cofactor C21, which is equal to -1 to the 1 plus 2 times the determinant of 2, 0, 1, 1, which is equal to -2. The third element is -1 to the 1 plus 3 times the determinant of 2, 0, 0, 2, which is equal to 4. I'm not going to write everything out, but we go through the same process for the rest of the elements and find they are equal to -1, 1, -2, 1, -1, -2. Alright, now we've got the adjoint, so it's easy to compute the inverse. The inverse is just the adjoint times 1 over the determinant, so it is equal to 0, 5, 0, 5, -1, 0.25, -0.25, 0.5, -0.5, -0.25, 0.25, 0.5. Alright, we've now learned to use the determinants to compute the inverse of any square non-singular matrix. And just to review, we've got 3 nice uses for the determinant. We can use it to determine if a matrix is singular, we can use it to solve a linear system of equations, and we can use it to find the inverse of a matrix. There are actually some other special things that we'll need a determinant for later in the course, so don't forget about them. But before we move on, let's talk a bit about what it means for a matrix to be singular. A singular matrix is a square matrix that is not invertible. That means you cannot find an inverse for it. A singular matrix can also be defined as a square matrix that has a determinant of 0, which is one of the reasons why it is great to be able to calculate the determinant of a matrix. If you calculate the determinant and find that it is 0, then you know that the matrix is singular and you'll never be able to find an inverse for that matrix. Let's look at this in practice to get a real feeling for what it means. Let's say we were trying to make some very simple predictions about the weather. Someone dropped you off in a strange town. You don't have any access to advanced computers. You don't have any access to fancy meteorological equipment. But you want to try to predict the weather anyway, or at least come up with enough of a prediction to decide whether or not you want to take an umbrella with you. So you pay attention to the weather for a few weeks. You keep some detailed notes on whether it's rainy or it's cloudy. You notice that if it is sunny on any particular day, there's a 90% chance that it will be sunny the next day. You also notice that if it's rainy on one day, there's a 60% chance that it will be rainy on the next day. We can encode this into a matrix. We'll call the matrix W for weather. W will be equal to 0.9, 0.4, 0.1, 0.6. It tells us that if it's sunny today, there's a 90% chance that it will be sunny tomorrow, and a 10% chance that it will be rainy tomorrow. On the other hand, if it's rainy today, there's a 40% chance it will be sunny tomorrow and a 60% chance that it will be rainy tomorrow. Let's look at how we would actually make use of W to predict the future weather. Let's say that today it is sunny. If we know it is sunny today, we can write a vector for today's weather that has a 1, then a 0. The 1 tells us there is a 100% chance that it's sunny today and a 0% chance it's rainy. If we multiply W times this vector, we get the vector 0.9, 0.1, which tells us there's a 90% chance it will be sunny tomorrow and a 10% chance it will rain. Similarly, if it is raining today, we should use the vector 0, 1 and multiply W times 0, 1 to find that there is a 40% chance of sun tomorrow and a 60% chance of rain. Okay, that's not super useful yet because that's what we already knew. But let's say you're actually planning a 3-day trip and want to know if you should take an umbrella. Let's say that it's sunny today. If it's sunny today, there's a 90% chance that it's sunny tomorrow. But what about the day after tomorrow? Well, since we know how weather on one day is correlated with weather the next day, we can simply multiply W times the weather tomorrow to compute the weather 2 days from now. We find that there's an 85% chance it'll be sunny 2 days from now and a 15% chance that it'll be rainy. If you're paying attention to how this works, you might also note that this is also completely equivalent to multiplying by W twice, or in other words, we can compute that the weather 2 days from now is equal to W squared times the weather today. Similarly, to find the weather 3 days from now, all we need to do is multiply W cubed times 10 to find that 3 days from now we should expect 82.5% chance of sun and 17.5% chance of rain. Alright, so far this math should look really familiar to you. It's basically the same approach that we took when we were looking at population dynamics. But let's follow our logic through a bit further and maybe ask some other questions. In this strange new town, with no qualified meteorologists, you're the first person to discover this relationship. So you go ahead and share it with the local radio station, and they start using this info to predict the weather. Great, we've made an advance. So let's say we went on that 3-day trip. When we get home, we want to decide whether or not we need to water our plants. On the way home, we're listening to the radio, and the weather forecaster tells us that there's a 90% chance of sunny weather tomorrow. If we don't have anyone to ask about what the weather actually was yesterday, how could we figure it out from the information that we've got? Well, we already wrote out that equation that a vector containing tomorrow's weather information can be computed by multiplying our W matrix times a vector containing today's weather. We know that the meteorologist uses this equation to estimate the weather tomorrow. So if we can invert this equation, we can figure out the weather vector that he started with, or in other words, the weather earlier today when we were out of town. We know this works because if we multiply both sides of our equations by W inverse, then W inverse and W will cancel out on the left-hand side of the equation, and we see that today's weather is equal to W inverse times our prediction for today's weather. Okay, so we need to compute W inverse. Earlier in the lecture, we learned that for a 2 by 2 matrix, we can compute the inverse by flipping the top left and bottom entries, putting negatives in front of the top right and bottom left entries, and multiplying by 1 over the determinant. Okay, so the determinant is equal to 0.9 times 0.6 minus 0.4 times 0.1, which is all equal to 0.5. Since the determinant is not 0, we know that W is not singular, and it does have an inverse. We also know that the inverse will be equal to 1 divided by the determinant times 0.6, negative 0.4, negative 0.1, 0.9, which is equal to 1.2, negative 0.8, negative 0.2, 1.8. Alright, so now we can use the inverse to figure out what the weather was today. The radio station predicted a 90% chance of sun for tomorrow, so our tomorrow vector is 0.9, 0.1, and we can plug in to find that today's weather equals 1.2, negative 0.8, negative 0.2, 1.8 times 0.9, 0.1, and then we multiply this out and we find that V today equals 1, 0, equals 1, 0, so that means it was sunny today. And that tells us that we need to go out and water our plants. Okay, good. That was not a singular matrix. Actually, just so we're clear, there's a typo in this slide. This bottom line should say V today equals 1, 0. We shouldn't have that matrix there. All right, continuing on. So that was not a singular matrix. What might be a singular matrix? Well, let's talk about predicting the weather quite a bit longer into the future. Specifically, let's talk about future predictions of the weather based on today's weather. We know that for tomorrow's weather, we just multiply W times today's weather. So if it's sunny, there's a 90% chance it'll be sunny tomorrow. And if it's rainy, there's a 60% chance it'll be rainy tomorrow. For the weather 2 days from now, we simply compute W squared times today's weather. So that tells us if it's sunny today, there will be an 85% chance it'll be sunny the day after tomorrow. And if it's rainy today, there's a 40% chance it'll be rainy the day after tomorrow. If we ask about 3 days from now, it's simply W cubed in the equation, and we find that 3 days from now, there's an 82.5% chance it'll be sunny if it's sunny today, and only a 30% chance it'll be rainy if it's rainy today. Now let's ask about 1 week into the future. Of course, 1 week is 7 days, so this time we simply put W to the 7th power in the equation, and now we see that if it is sunny today, there's an 80.16% chance it'll be sunny 1 week from now, with a 19.88% chance it'll be rainy. And if it is rainy today, there's a 79.38% chance it'll be sunny 1 week from today, with only a 20.63% chance of rain. If we look at this, we can see that whether it is rainy or sunny today, there's about an 80% chance it'll be rainy a week from now. This tells us that the weather today actually gives us very little information about the weather 1 week from now. And if we ask about the weather a month from now, we need to take W to the 30th power, and at least within the rounding errors of my computer, this tells us that there is exactly an 80% chance it'll be sunny 1 month from now, whether it is sunny or rainy today. This should jibe with what you know about the weather. The atmosphere is chaotic, so we cannot predict the weather with any certainty 1 month from now. We simply have to rely for predictions that far out by using the average climate. But what if, when we were coming home from our trip, all we heard was the radio station's long-term forecast? We turned on the radio just a little too late, so we didn't hear what they said the weather would be tomorrow, or even 1 week from now. But we did hear them say that the weather 1 month from now has an 80% chance of sunshine. In that case, we know that we can write an equation saying that W to the 30th times the vector for today's weather equals 0.8, 0.2. But how can we solve it? Well, let's go ahead and define a new matrix that we'll call M. M will be a matrix that predicts the weather 1 month from today if we give it the weather today. So M will be equal to W to the 30th, which we figured out on the last slide is equal to 0.8, 0.8, 0.2, 0.2. Alright, so we can now plug that into the equation above, and we have that M times the weather today is equal to 0.8, 0.2. Now all we need is the inverse of M, and we can calculate the weather today. But there's a problem. The determinant of M is 0.8 times 0.2 minus 0.8 times 0.2, so it's equal to 0. If the determinant of M is 0, then the inverse of M is equal to 1 divided by 0 times 0.2, negative 0.8, negative 0.2, 0.8. Since 1 divided by 0 is undefined, the inverse is undefined. We cannot compute an inverse because M is singular. This is what it means to be singular. We cannot compute an inverse. If we look at M, we can see why we cannot compute an inverse. No matter what vector for today's weather that we multiply M by, we will get the same answer. If we plug in a sunny day, we get an 80% chance of sun a month from now. If we plug in a rainy day, we get an 80% chance of sun a month from now. If we say that we aren't sure what the weather was today and we think there's a 50% chance it was rain and a 50% chance it was sunny, we get an 80% chance of rain a month from now. Since we get the same answer despite putting these multiple answers in, we cannot figure out from the answer what our original vector was. A singular matrix is thus like a function that doesn't have an inverse. If you can get the same answer for multiple inputs, you can't get a well-defined inverse. And this makes sense for our weather information. We know that today's weather gives us no useful information about what the weather will be a month from now. So if we want to predict the weather a month from now, we just default to using the long-term mean. But if all we're really doing is predicting the future from that long-term mean, there is no way that hearing the weather announcer tell us that 1 month from now there's an 80% chance of sun can tell us anything about what today's weather was. Alright, that's it for this toolbox. Don't forget to take the mini quiz online before class.